So we're building up the algebra of derivatives, but this is the first time we've seen an example like this. So we have h of x equals sine of x squared, and we want to get the first derivative of this thing. Now we know how to differentiate the sine function, that's just the cosine, and we know how to differentiate x squared, that's just 2x. But what are we supposed to do with a composition of two familiar functions? Well, this is what the chain rule does. So here's a statement of the chain rule. If h of x is given by some composition of functions, f of g of x, then we can get the first derivative of that by taking f prime and evaluating it at g of x, and then multiplying by g prime of x. Now, because it involves function compositions, it's a little bit tricky just to apply the chain rule. And we will finish this example at the end of the video, but first, let's derive the chain rule and find out why it works in the first place. So we have this theorem that we call the chain rule. If h of x is f of g of x, then h prime of x is f prime evaluated at g of x, then multiplied by g prime of x. So to get the proof started, we say let h of x be this function composition f of g of x. Next, we need to write down the derivative using the limit definition of the derivative. And so we're using the limit definition where we say, take the limit as x goes to a of h of x minus h of a over x minus a. And that's going to give us the derivative of this function h evaluated at some specific value of x that we call x equals a. So this is just notationally the most convenient form of the derivative limit for this proof. So the next thing to do is sub in the definition of h. And there it is, h is f of g of x, so we just sub in x for the argument in that first term, a for the argument in the second term. But notice what we're looking at in the numerator here. I have a variable value, g of x, in the parentheses of my function f. So I have f evaluated at some variable value. And then in my second term, I have f of some fixed value, g of a. Well, if I have f of some variable value minus f of some fixed value, if I were to put that variable value and fixed value in the denominator, it would build a derivative. It would build a derivative of f. So what we're going to do here is put a g of x minus g of a into the denominator so we can recognize a derivative there. But this has some side effects. We can't just put a g of x minus g of a in the denominator without compensating for it. So here's our next step. We put a g of x minus g of a into the denominator of that first chunk. So in other words, we divided by g of x minus g of a. Then we compensate by multiplying by g of x minus g of a in the second term. And again, we still have a factor of x minus a floating around in the denominator. Now to reiterate, what we have in this first numerator is f of a variable minus f of a constant, then divided by that variable minus that constant. And in our limit, as x goes to a, our variable quantity g of x is approaching our fixed quantity g of a. That is exactly the definition of a derivative. So it's going to give us f prime, but in particular, it gives us f prime evaluated at this fixed constant, g of a. So that's f prime of g of a. Notice what we have in our second fraction here is precisely the definition of the derivative of g with respect to x, or g prime of a. So that's really the essence of the proof. We just found that h prime of a is f prime of g of a times g prime of a. But there are a couple small details that we have to wrap up. So first, there's a logical gap in the proof. And the issue is g of x minus g of a could be exactly equal to 0 when x is close to a. If that happens, this fraction is undefined and the proof is broken. So we need to comment on that. And we say this statement that we derived is only true if g of x is not equal to g of a when x is close to a. But then we need to figure out what happens if g of x is equal to g of a when x is close to a. Well, if g of x has the same value of g of a when x is close to a, we can look at the definition of the derivative again. So I just want to highlight this piece right here inside the limit. That's giving us g prime of x. If g of x was equal to g of a, it's clear that the derivative is equal to 0. And if the derivative of g is equal to 0, that means g is a constant function. But if g of x is a constant function in the neighborhood of x equals a, then f of g of x is a constant. In other words, h of x is a constant function, so the derivative of h is going to be 0. All right, but that means that we're still satisfying the chain rule, because when g prime is equal to 0, according to the chain rule that we already wrote down, when g prime is equal to 0, h prime should be equal to 0. So even though that case was troubling, it turns out it was still consistent with the chain rule. Now, the final step we're going to make here is that we don't really like having the chain rule written in terms of a specific value of x that we called a, but that a really was just some arbitrary value, so we can replace it with an x. And that gives us this familiar statement for the chain rule h prime of x is f prime of g of x times g prime of x. Okay, so now we know why the chain rule is true. And again, this can be really tricky to apply just because function compositions are a tricky thing to think about. So let's finish the example that we started in the introduction. So we're given a function h of x equals sine of x squared. And we can approach this problem by explicitly identifying the f and g in this function composition. So we're going to say the outer function here is f of x equals sine of x. And the inner function, that's g of x, is equal to x squared. And you can just verify that this function composition is working as it should by computing f of g of x. Well, that's just f of x squared, because g of x is x squared. And f of x squared means you replace all the x's with x squareds, and I get the sine of x squared. Okay, so we've correctly identified the functions that are involved in the composition. Now it'll also be handy if I make a note of the derivatives of these functions. So f prime of x is just cosine x, and g prime of x is 2x. And now we can apply the chain rule. So h prime of x turns out to be f prime evaluated at g of x, then multiplied by g prime of x. So here's f prime, that's cosine x, but I need to evaluate that at g of x. In other words, I need the cosine of x squared. Then we tack on this factor, g prime of x, which turned out to be 2x. Now this answer is a little bit nicer if we put the 2x in front. So I have 2x cosine x squared, and we're done with the problem. Okay, so we solved the problem, but there's a way more intuitive way to think about what we're doing here. So in the next video, we get serious about solving chain rule problems efficiently and intuitively. I'll post a link to that video at the upper left, and I'll see you there.